Hey everyone, welcome to your first video of 2021. We are going to be talking about lesson 14.2, attributes of polynomial functions. And the word attributes really just means key features. So we're going to be talking about that, and it starts on page 231 of your Springboard book. So go ahead and grab that to follow along. You'll also want a pen or a pencil, and you will definitely want a graphing calculator because we're going to be looking at some different graphs. Okay. So first up, lesson 14.2, some attributes of polynomial functions. The learning targets are that we are going to sketch the graphs of cubic functions. So unit 2 was all about quadratics. Unit 1 was all about linear functions, right? Now we're going to be moving into unit 3, which is about polynomials, which could be cubic functions, quartic functions, but it also could include some quadratic and linear functions as well, okay? Then we're also going to identify the end behavior of polynomial functions, okay? All right, so I'm going to skip over some of this information here, but basically what you need to know here is some of these terms about a polynomial function, okay? And we've already talked about the fact that a polynomial is in standard form when all like terms have been combined and the terms are written in descending order by exponent. Okay, so you'll never see like a x squared in front of an x cubed. That's not correct. That's not standard form. Okay. But something else that's important to note here is that the highest power or exponent, n, is the degree of the polynomial function. Okay, so that's another important piece there. And if we take a look at this example they gave us, we have 7x to the fifth plus 2x squared minus 3. So first of all, that is in standard form because we have x to the fifth, then x squared, then no x, right? So it's in descending order. We're good to go, okay? We know that each of these are called a term. So this polynomial has 3 terms. We know that this last term is called your constant, okay? And then what might be new here is that this is going to be whatever your first term is, the number out front is your leading coefficient. And on the first term as well, whatever the exponent is, or the highest power, that is the degree of the polynomial, okay? And we're going to refer to the degree of the polynomial quite often, so that's an important term to know, okay? Then over here, if you guys look at the math term, it does talk about some common types of polynomial functions. So you have your constant, which would be degree 0 because there is no exponent, right? You have your linear, which would just be x. So that has a degree of 1. You have your quadratic, which we just studied, x squared. So that has a degree of 2. Excuse me. You have a cubic, which would be x cubed. So that has a degree of 3. And you have quartic, which would look like x to the 4th. So that has a degree of 4. So that's where that comes from. And again, as long as it's in standard form, you should be able to see that. Okay. It says down here, various attributes of the graph of a polynomial can be predicted by its equation. Here are some examples. So first thing, the constant term is the y-intercept. So if we look back up at this example, -3 would be your y-intercept. Okay. Then it also says here that the degree tells that the maximum number of x-intercepts that the graph of the polynomial can have. So again, our degree is this highest exponent. So now we know that the graph could cross through the x-axis or have 5 x-intercepts. Okay. And then last thing, the degree of the polynomial also gives you some information about the shape of the graph at its ends. Okay, so we're going to talk about this a little bit later and throughout the week, but whether it's an odd number or an even number will help us talk about the end behavior. Okay. All right, cool. Let's go ahead and keep moving. Okay, so this was actually a graph that was supposed to be talked about in a previous lesson, but we skipped that lesson. So we're just going to go ahead and look at this graph as an example, okay? And the first thing it says is to name any relative maximum values and relative minimum values. So when we were talking about quadratic functions, right, we saw some like this and some like this, these parabolas, okay? And we knew, okay, if it opens upward, it's going to have a minimum value. And if it opens downward, it's going to have a maximum value. Okay, and it's the same idea now. The only reason they're called relative is because now we may have polynomials that have quite a few minimums and maximums. Okay, so I find it's helpful if you just think of relative maximums as all of the hills and relative minimums as all of the valleys. Okay, so for example, this one would have a relative minimum at this valley and at this valley, but it would have relative maximums at this hill and this hill. So that's, whoops, the only reason they're now called relative is because there may be more than one. Okay, so for example, in this one, we have a relative maximum right here and a relative minimum right here. So the relative maximum was the hill and the relative minimum was the valley. Okay. Then this next part is asking us to name X and Y-intercepts. So our X-intercepts, remember, are just where it crosses the X-axis. So we would have one here and here in green. And then last, Y-intercepts is just where it crosses the Y-axis. So that would be here. Okay. So those are the first four attributes or key features we're going to talk about: relative maximums, minimums, and then X and Y-intercepts. Okay. So number 4 here says, using a graphing calculator, sketch the graph of 2x cubed minus 5x squared minus 4x plus 12. So first of all, that's in standard form. You're good to go. If you would like, you could pause the video and plug that into your graphing calculator. But you should get something that looks like this in your screen, okay? And then what you could do is just go ahead and kind of estimate where those, so on the next page, numbers 5 and 6 ask for what are the relative maximums and minimums and what are the X and Y-intercepts. So you could go ahead and kind of estimate those. I will show you guys in your calculator how to actually find those exactly. But I'll do that in class during the Zoom, okay? So to start out, I know I have a relative maximum here. So we could probably estimate that at about, I don't know, maybe we would say like 12.5, 12.6, okay? Because we're saying how high it is, okay? Then this one here, your relative minimum, we would say it's probably at 0. Then my x-intercepts, I could say, is probably at negative 1.5, 1.5, and at 2. And then my y-intercept, if I wanted to estimate that here, I would maybe say that that's at 12. Okay, so again, whoops, I'm just estimating, but you guys, I will show you how to find the exact number tomorrow in class, okay? All right, cool. So the next thing I want to talk about really quickly is, now we're on page 233. If you look at number 11, it says, using the graphs you have sketched in this lesson to speculate the minimum number of times a cubic function must cross through the x-axis and the maximum number of times. So if we go ahead and look at both of those graphs, I can tell that this definitely crosses through the x-axis once, and then it looks like it kind of bounces off once. And this crosses through once and kind of bounces off once as well. Now, they won't all do that, but these two happen to. So I would say that the minimum number of times that those functions, and both of those, I don't know if you guys caught this, both of those were actually cubic functions. So it was negative 4x cubed and 2x cubed. Okay, so that was the degree, both degree 3. And the minimum number of times it would have to cross through the x-axis would be once. But if we look back here, it said right here that the degree tells you the maximum number of x-intercepts, or the maximum number of times it will cross through the x-axis. So that maximum number of times would be 3, because that was the degree. Okay. All right, awesome. So next thing we're going to talk about here is the end behavior. Okay. And the end behavior describes what happens to the graph at the extreme ends of the x-axis. So basically, as x approaches negative infinity and as x approaches positive infinity, what is happening to y? Okay, so it is saying if we examine our graph from item 1, so if we go all the way back here and we examine this graph here, okay, and you guys can take a look at that. It's saying to describe the end behavior of the graph, you would say that the left side of the graph increases or points upward continuously, and the right side of the graph decreases or points downward continuously. Okay, but we're going to use a mathematical notation called arrow notation to describe the end behavior, and it's always going to be set up like this. Okay, but these numbers or these values are going to change. Okay, so I'm just going to go ahead and write it out as x approaches negative infinity, which means actually as we approach the left side. Okay, because think about that. As you approach negative infinity on the x-axis, that is going this way. Okay, so as we do that, what's happening to y? So we're going to say y approaches, and basically that means as we move this way, what's happening to our graph? And it's pointing down. So we would say y approaches negative infinity. Okay. Then you're going to do the other side as x approaches positive infinity, which that's obviously going to be the right side. Because remember, your x-axis goes left and right. So now we're going to go as we approach positive infinity on the x-axis, what's happening to our graph, and it's pointing up. And it's going to continue on in that direction for forever, so we would say y approaches positive infinity. Okay. Okay, let's go ahead and try some more with that. Okay. So it says here to examine the end behavior of 3x squared minus 6. So the first thing I would do is graph that in your graphing calculator. And you should get a graph that looks like this. And we know it's going to keep going up in both directions. So we are going to say, as x goes to infinity, what is the end behavior, or what behavior does the function have? So let's say as x approaches infinity, because we're going to use our arrow notation. And remember, infinity, positive infinity, is to the right. So what's happening as x moves to the right? Well, your graph is going up. So we would say y approaches positive infinity. And you can put the plus sign there if you want to, but you really don't need to. You can just put positive infinity or just the infinity sign. Okay. Then let's go ahead. It says, how is the function behaving as x approaches negative infinity? So now we're going to say as x approaches negative infinity, and that would be to the left, negative infinity, and this side is also pointing up. So we would say y approaches positive infinity. Okay, so this right here is the end behavior, and it tells us that both sides are pointing up because they're both going towards positive infinity. And that is exactly what's happening here. Okay. So then it says, it is possible to determine the end behavior of a polynomial's graph simply by looking at the degree of the polynomial and the sign of the leading coefficient. Use a graphing calculator to examine the end behavior of polynomial functions. In general, sketch each given function. Okay, so normally in class, I would have you guys put these in your graphing calculator and sketch them all out. But for the sake of time, I've already sketched them out here, okay? So I want you to maybe pause the video and just kind of check them out or graph them in your calculator on your own. But we have x squared, negative x squared, x cubed, negative x cubed, x to the fourth, negative x to the fourth, and x to the fifth, negative x to the fifth, okay? And what we're going to talk about is, first of all of the positive ones. You see that? They're all on the left side. And all of the negative ones are on the right side. Okay? And as we know from quadratic functions, the negative out front just reflects the graph over the x-axis. And that is the same for all of these. Okay? Then what I've also done is highlighted ones that have similar shapes. So like A and E have a similar shape. B and F have a similar shape. C and G have a similar shape, and D and H do. Okay. And then I want you guys to think, which graphs have an end behavior in the same direction on both sides? Okay, so we just talked about end behavior. So which ones have, which graphs have the same end behavior on both sides? Meaning they're both pointing up or they're both pointing down on each side. So you should be thinking A, both pointing up, B, both pointing down, E, both pointing up, and F, both pointing down. Whoops. Okay, so what I want you guys to do is look at the degree of each of those functions. So A, the degree is 2. B, the degree is 2. E, the degree is 4. And F, the degree is 4. Okay, so what we're going to find in the next couple of days is that the functions that have the same end behavior also have an even degree. 2, 4, 6, 8. Okay, so that's going to be an important factor. All right. Then the next question obviously says which graphs have an end behavior in the opposite direction. So that would be C, 1 points up, 1 points down. D, 1 points up, 1 points down. And then G, 1 up, 1 down, and H, 1 up, 1 down. Okay, so C, D, G, and H. And obviously all of these, so degree 3, x cubed, negative x cubed, degree 3. X to the 5th, negative x to the 5th, degree 5. So all of these 3 and 5, 3, 5, 7 are all odd degrees. So that's another thing that will help us in determining what will this polynomial look like. Okay. So those are some of the important attributes that we're going to be talking about. We have relative minimums, relative maximums, the x-intercepts, y-intercepts, whether it is a positive or negative lead coefficient, whether it is an even degree or an odd degree, and the end behaviors. Those are all key features or attributes of polynomials that we're going to be focusing on. Okay? So we'll talk about this more during our Zoom tomorrow, and have a good one. Bye-bye.